Next one is the concept of vaporization. Vaporization, evaporation, rate of vaporization, rate of condensation, and vapor pressure is there. So vaporization means conversion of liquids into vapors above its boiling point is known as the vaporization. Evaporation is the conversion of liquids into vapors below its boiling point. For example, here you can take the one container. In this container, you can take the one liquid, and whatever the molecules, liquid molecules are present at the surface of the liquid. These liquid molecules are having more kinetic energy than the molecules present in the bulk. For example, here red mark is there. Think that this red mark liquid molecule is present in the bulk. This liquid molecule is attracted by the other liquid molecules from its surroundings, so that this liquid molecule is having the less kinetic energy. But what are the liquid molecules are present at the surface of the liquid? They are attracted by the downside and left and right side molecules only. But above this layer there is no liquid molecules, so that these liquid molecules are having the residual forces. Due to this more residual forces, these liquid molecules can overcome the attractions between these liquid molecules and other liquid molecules. These liquid molecules will convert into vapor state. These are converted to which state? Vapors state. Means conversion of liquid into vapors above the boiling point is known as vaporization. And evaporation also is there. The evaporation also the similar process, but in evaporation, conversion of liquid into vapors below its boiling point is known as the evaporation. And both vaporization and evaporation process are the surface phenomenons. Means as the surface area is increases, evaporation and vaporization is increases. And here both vaporization and evaporations are explained by kinetic molecular theory. So, according to kinetic molecular theory, the average kinetic energy of these liquid molecules is the same, but the liquid molecules which are present at the surface of the liquid, those are having more kinetic energy. The liquid molecules present in the bulk, those are having less kinetic energy. So here, whenever more kinetic energy containing liquid molecules will escape from the surface of the liquid, as a result, the average kinetic energy of these liquid molecules is decreases. So that evaporation and vaporizations are the cooling effects. And the next one is the rate of vaporization. So rate of vaporization means the number of liquid molecules are converted into vapor state per unit time is known as the rate of vaporization. And rate of condensation. So rate of before discussing about this rate of condensation, we will see the condensation process. And we know that liquid molecules will leave the surface of the liquid and converts into vapors. These vapors are having the more kinetic energy. The more kinetic energy containing vapors will collide with the walls of the container. So when these can collide with the walls of the container, these liquid gas molecules can lose the energy. As a result, those vapor molecules will come towards the surface of the liquid. So then the gases are converted into liquids is known as the condensation process. So rate of condensation means The number of vapor molecules are converted into liquid state per unit time is known as the condensation, rate of condensation. So whenever the rate of vaporization and rate of condensations or takes place equally, we will get the equilibrium. So means at equilibrium, rate of vaporization and rate of condensations are equal. So when these two are equal, at that time, some of vapor molecules can exert the pressure by the collisions of vapors with the walls of the container is known as the vapor pressure. Means the pressure exerted by the vapors at equilibrium is known as the vapor pressure. So this is about the vaporization, evaporation, rate of vaporization, rate of condensation, and vapor pressure. And next one is this concept we can apply for the Raoult's law. And Raoult's law, two methods are there: Raoult's law for volatile liquids and Raoult's law for non-volatile liquids. First we will see the Raoult's law for volatile liquids. So this definition is very important for one more question. The partial vapor pressure of each component of the solution is directly proportional to its mole fraction present in the solution. And we know that vapor pressure means pressure exerted by the vapors at equilibrium is known as the vapor pressure. Partial vapor pressure means pressure exerted by the a single component is known as the partial vapor pressure. Partial vapor pressure of the component is directly proportional to what? Mole fraction of the solution. So we will discuss by taking the example. Now you can take the one container. So in this container you can take the two are the volatile liquids. Okay, for example, A and B are the volatile liquids. So volatile liquids means the liquids which are having more evaporating power is known as the volatile liquids. For example, you can take the water. Okay, water and petrol. So at room temperatures and at a normal conditions, out of this water and petrol, the petrol is easily evaporate, so that it is a highly volatile liquid, and this one is a less volatile liquid. Even this liquid water molecule also will volatile, but at a high temperature. At a normal temperature, the petrol is easily converted into vapor state, so that petrol is a highly volatile liquid and water is the less volatile liquid. Okay, leave that. Now volatile liquids, take the two liquids A and B. These two are the volatile in nature. Now here component A and component B are there, and the pressure exerted by this component A, you can take the PA, and pressure exerted by the component B, you can take the PB. Now the mole fraction of the component A, you can take the XA, and the mole fraction of the component B, you can take the XB. Now at normal conditions, this component A will converted into vapor state. At vapor state, this component A can exert the some pressure. That pressure is known as the partial pressure of the component A. In the similar way, component B also is converted into vapor state. In vapor state, this component B can exert the some pressure with the collisions with the walls of the container and exert the pressure, that is the partial pressure PB. And how much pressure exerted by the component A and component B is depends upon the mole fraction of the component A and component B. Means mole fraction, already we discussed. Mole fraction means the ratio between number of moles of one component to the total number of moles of all components. For example, if you take the mole fraction of the component A, then number of moles of component A by number of moles of component A plus number of moles of component B. If in case, if component A in the solution is the more, then pressure exerted by the component A is the more. If in case component B in the solution is the more, then pressure exerted by the component B is more than the component A. Means the pressures exerted by each component is directly proportional to its mole fraction. Now we'll see, means PA is the partial pressure of component A is directly proportional to what? Mole fraction of the component A. Then by removing this proportional, we can get the proportionality constant or partial pressure of pure component. PA is equal to PA naught into XA. Here PA naught, this naught indicates in the form of pure state, and PB partial pressure of the component B is also directly proportional to mole fraction of the component B. By removing this proportionality, we can get the PB naught. So here PB naught, the partial pressure of the component B in the form of pure state. Means here we discussed in container we are taking the both A and B. If in case, if it in another container, if you take the only one component, it can exert the pressure, that is the PA naught. Means pressure exerted by the component A in the form of pure state is the partial pressure of component A in pure state. So if you take a component B in another container, only component B, this one also can exert the pressure, that is the PB naught. So naught indicates what? In the form of pure state. Uh, Now the total pressure is exerted by these two volatile liquids is called PA plus PB. Then total pressure is equal to, we know that PA is equal to what? PA naught into XA plus PB naught into XB. Then total pressure is equal, here PA naught is the partial pressure of pure component A, and here 1 minus XB is the mole fraction of A, and XB is the mole fraction of the B. So in mole fraction we discussed XA plus XB is equal to 1, means the sum of mole fractions of component A and component B is equal to 1. But if XA is equal to 1 minus XB, so this only we substituted in this equation, means XA is in place of XA 1 minus XB. So if you simplify this, we can get the PA naught plus PB naught minus PA naught into XB. And here this is the equation, is a very important equation for the problems, and you can write the parameters here. PA naught is the vapor pressure of pure component A. So PB naught is vapor pressure of pure component B, and we know that XA is the mole fraction of component A and XB is the mole fraction of the component B, and this one we can draw in a graphical representation. Now see, so on a y-axis you can take the vapor pressure, on x-axis you can take the mole fraction. Now here 1, 2, 3 are there. 1 indicates PA, indicates a solute. Pb indicate the solvent, and total pressure Pa plus Pb, third one is the solution. So from this graphical representation we can conclude the 3 points. One is the total vapor pressure over the solution is determined by either XA or XB. It indicates the total vapor pressure over the solution is depends upon the amount of the component A or amount of the component B. Out of these two, any one factor can influences the vapor pressure of the solution. And next one more is total vapor pressure over the solution is depends only on the factor XB. See here XB nothing but a solute, means whether solute amount is increases, vapor pressure is decreases. When a solute is increases, sorry, decreases, vapor pressure is increases. Okay. And next third point is whether component mole fraction of the A or mole fraction of the B increases, the vapor pressure is increases. Component A and component B are decreases in the solution, vapor pressure is also decreases. And this Raoult's law is applicable for only ideal solutions. Raoult's law is applicable for only ideal solutions. And one more thing, this Raoult's law is applicable for only dilute solutions. You have to remember it is applicable for only ideal solutions, dilute solutions. And one more is this Raoult's law is applicable for only the solutions which contains non-volatile liquids. And one more is, so in Raoult's law the solute neither associate nor dissociate with solvent molecules. So this is about the Raoult's law for volatile liquids. And the second law, the Raoult's law for non-volatile liquids. So don't get the confused. So in examination for 1 mark or 2 marks, they ask the Raoult's law and Raoult's law for volatile liquids and Raoult's law for non-volatile liquids. So they will mention, write the Raoult's law for volatile liquids, or they may mention Raoult's law for non-volatile liquids. So till now we discussed Raoult's law for volatile liquids. Now we will see the Raoult's law for non-volatile liquids. So definition is the relative lowering of vapor pressure of a dilute solution which contains non-volatile solute is directly proportional to the mole fraction of the solute is known as the Raoult's law. Now see here also take the one container. So in this container first you can take the only pure solvent. You can take the water molecules. Okay, pure water. So these pure water molecules boil, and whatever the liquid molecules are present on the surface area, those all the liquid molecules can gain energy and goes to vapor state. And they can collide with the walls of the container and exert the pressure that is known as the vapor pressure. Now before adding the solute, if only the pure solvent can exert the some pressure, that you can take Pa naught is equal to, you can assume 1 atmosphere pressure. So to exit the 1 atmosphere pressure, here how many liquid molecules are converted to vapor state? First count 1 2 3 4 5 6 7 8 9 10. Okay, to exert the pressure by these solvent molecules 1 atmosphere, 10 water molecules are converted into vapor state. Now you can add the one solute. That solute should be non-volatile. Which type of solute? Non-volatile. So volatility means the tendency to evaporate the or to convert the liquids into vapors. Non-volatile means the liquids or the solids which does not converts into vapor state or gas state is known as the non-volatile solute. So after adding the non-volatile solute, some of the after adding the solute non-volatile solute to the liquid, some of the solvent molecules are replaced by the solute molecules. For example, the solute molecule is replaced by the solute, and this one also is there, and this one also is replaced by the solute molecules. Means the red color circles are the non-volatile solutes, and these normal circles are the solvent molecules. Now you can heat this solution. So now how many liquid molecules are present on the surface of the liquid? 1 2 3 4 5 6. Means out of 10, only the 6 molecules will convert into vapor state. At the time, this component A can exert the pressure more than the 1 atmosphere or less than that 1 atmosphere. So obviously it is less than 1 atmosphere. Means by adding the non-volatile solute to the pure solvent, the vapor pressure of this pure solvent is decreases. This is known as the lowering of vapor pressure. Okay, that we will discuss later. Okay, so did you get a clarity here? So vapor, the pure solvent is having more vapor pressure, and after adding the non-volatile solute to the solution, vapor pressure of the pure solvent is decreases. So it indicates after adding the solute to the solvent, it becomes to solution. Means solution is having a less vapor pressure than pure solvent. Okay, the solution has less vapor pressure than the pure solvent. So next one is a lowering of vapor pressure. Lowering of vapor pressure. The pressure decreased by the addition of non-volatile solute to the pure solvent is known as the lowering of vapor pressure. Otherwise, the difference between vapor pressure of pure solvent and vapor pressure of solution is known as the lowering of vapor pressure. Here, for example, vapor pressure of pure solvent is a 1 atmosphere P naught minus the vapor pressure of the solution. So here P naught indicates vapor pressure of pure solvent and P indicates vapor pressure of the solution. So the difference between the vapor pressure of pure solvent and vapor pressure of the solution is known as the lowering of vapor pressure. And one more is a relative lowering of vapor pressure. Means it is the ratio between lowering of vapor pressure and vapor pressure of the pure solvent is known as the relative lowering of vapor pressure. Now see, P naught minus P is the lowering of vapor pressure and P naught is the pressure of vapor pressure of the pure solvent. So the ratio between lowering of vapor pressure to the vapor pressure of the pure solvent is known as lowering of relative lowering of vapor pressure. So that only we discussed here. Now see, Pa naught. Now this is the pure solvent and this one is the solution. Here 1 2 3 4 5 molecules will convert into vapor state and exert the pressure, that is the vapor pressure of the component A in pure state. Now we added the non-volatile solute. Okay, non volatile solute we added. So how much you add, there is no increase in the vapor pressure of this solution. Okay, now see the definition. Raoult's law for the non-volatile: the relative lowering of vapor pressure of a dilute solution which contains non-volatile solute is directly proportional to what? Mole fraction of the solute. Now p naught minus p by p naught is what? Relative lowering of vapor pressure. It is directly proportional to what, or is equal to mole fraction of the solute. And we know that mole fraction of the solute equation is what? Mole fraction of solute is equal number of moles of solute by number of moles of solute plus number of moles of solvent. Number of moles of solvent. Now all again we know that number of moles of solute equation is what? Weight by gram molecular weight. And for this solute, number of moles of solute, you can take weight WB, you can take gram molecular weight MB, you can take. And number of moles of solvent is what? Number of moles of solvent is equal WA by MA. Now substitute these equations in mole fraction of the solute. So P naught minus P by P naught is equal. So number of moles of solute is what? Weight by gram molecular weight into, here we can get the MA by WA. This is the equation to calculate the Raoult's law. Means from this one we may calculate the partial pressure, weight, molecular weight of the solute and solvent. And you know the parameters now. Here P naught is equal vapor pressure of pure solvent. P indicates vapor pressure of solution. And next one, WB is equal weight of solute. MB is equal gram molecular weight of solute. Next one, MA gram molecular weight of solvent. And MB, sorry, WA is weight of solvent. Okay, so this is about the Raoult's law for non-volatile liquids. And one more important point is, and volatile liquids, the partial pressure of the gas is equal to mole fraction into total pressure. This you have to remember. And PB is equal to mole fraction of the B into total pressure. These two equations also you have to use in the problems. Okay, so this is about the Raoult's law. And next one is the ideal solutions are there.